Welcome to this session of Materials Engineering. Myself, Anirban Sarkar, Assistant Professor, Department of Mechanical Engineering of JS College of Engineering, Kolkata. Today's topic, we will discuss about that imperfections of metal. So first of all, in this today's session in imperfection of metals, the key issue to be addressed, what are the solidification mechanism first of all, what are the defects arise in solid during solidification or either maybe during cold and hot working, and can the number and type of defects be varied and controlled? How do defects affect materials property, and are these defects are undesirable or not? So first of all, let's start with the solidification of pure metal. The solidification occurs by the nucleation and growth of crystal in the melt. So whenever the material or the metal is extracted from its ore, it is in the liquid form, and slowly it will come to the room temperature. Then the first step of in the solidification is the formation of nuclei. The nuclei can be regarded as a small cluster of atoms having the right crystalline arrangement. When the melt is cooled below its melting point, the nuclei begin to form in many parts of the melt at the same time. And this rate of nuclei formation depends on the degree of undercooling or supercooling, and also on the presence of impurities which considerably facilitate nucleation. At temperature below the melting point, a nuclei has to be a certain minimum size called critical size, so that it will grow. The critical size is the greatest near the melting point, but the probability of forming such large nucleus is less. Particles smaller than the critical size will be dissolved by the vigorous bombardment of neighboring atom and can now grow gradually. These are called embryos. When the temperature is lowered, the vibration of atom gradually decreases, increasing the chance of survival of the small clusters of atoms, and therefore the critical size of nucleus decreases with decreasing temperature or increases degree of undercooling. Hence, at lower temperature, nuclei became progressively smaller in size, but the number greatly increases. Growth of nuclei occurs by diffusion process, which is also a function of temperature, and hence the rate of nucleation and the rate of growth are function of temperature. It is also clear that some degree of undercooling is necessary to start the solidification, that is nucleation. The extent of undercooling varies from metal to metal and also depends on the impurities in the metal. In the nucleation and growth of the crystal as shown, there are four figures. That is, First of all, that is the nucleation of crystal is shown. At the solidification temperature, atoms from the liquids such as molten metal begin to bond together and start to form crystals. The moment a crystal begins to grow is known as nucleus, and the point where it occurs is the nucleation point. The second figure shows a crystal growth. When a metal begins to solidify, multiple crystals begin to grow in the liquid. In the third figure, that is number C, it is shown irregular grains form as crystals grow together. The final size of individual crystals depend on the number of nucleation point and its orientation also. Depending on the orientation, the grain size may be irregular and may differ from one another. And number D figure or number 4 figure shows grain boundaries as seen in microscope. When the crystal now increasing in size by the progressive addition of atom and grow until they impinges upon adjacent growing crystals. So this is how in the solid, when the material is solidified from liquid state to solid state, the nucleation and growth of the crystal occurs. Next, that is dendrites. In metals, the crystals that form the liquid during freezing generally follow a pattern consisting of main branch with many appendages. A crystal with this morphology slightly resembles a pine tree and is called a dendrite, which means branching. The formation of dendrites occurs because crystal grow in definite plane due to crystal lattice they create. The figure, this is the figure of a dendrites of a cubical crystal. The mechanisms of dendritic growth is as follows. If the metal has a cubic lattice, the nucleus has a number of equivalent crystallographic direction along which crystal growth may occur. A considerable amount of latent heat is evolved in the direction of crystal growth, causing the temperature of the adjacent liquid to rise. This temperature may exceed the freezing temperature of metal, so that further growth of crystal in this direction will be stopped. In a perpendicular direction, the liquid region will have a lower temperature. Since there has been no crystallization and consequently no heat evolution, hence the crystal will grow in new direction, that is from point A to point C, until heat is dissipated from the initial region of crystal growth. Now, when the temperature of this region drops to a sufficient value below the freezing point, the crystal will assume its original direction of growth until it reaches to the next point, that is P, where again the temperature will rise and further growth of the crystal will stop. Then again growth of crystal occur in the direction perpendicular to the original direction of growth. This sequence of process leads to finally the structure characteristics of dendrites. Usually cast components show dendritic structure and hence dendritic structure typically as of a cast component. So whenever material is first is extracted from its iron ore, from ore, not only iron, that is from ore. So first of all, it will be in liquid state, and when it is solidifies, that is called the casting process, and it is molded in a suitable, by making suitable mold. So where generally this, by these mechanisms of dendritic growth, the materials is solidifies. Next is shrinkage. Material contracts or shrink during solidification and cooling. Shrinkage is the result of concentration of liquid as it cools prior to its solidification. Contraction during phase change from a liquid to solid, and contraction of solids as it continues to cool to ambient temperature. Shrinkage can sometimes cause cracking to occur in component as it solidifies. Since the coolest area of a volume of liquid is where it contracts a mold or die, solidification usually begins fast at these surfaces. As the crystal grows inwards, the material continues to shrink. If the solid surfaces is too rigid and will not deform to accommodate the internal shrinkage, the stresses can become high enough to exceed the tensile strength of the material and cause a crack to form. Shrinkage cavitation sometimes occurs because as material solidifies inwards, shrinkage occurs to such an extent that there is not enough atom present to fill the available space and a void is left. Next, the thing is that we will discuss, that is imperfection of solids. So as we know or just discussed, that when the material is solidified, there is always a tendency or there is always a void present in the solidified material. So this gives the raise the imperfections, or these are the imperfections in solids. And in this chapter we need to know that there is no such things as a perfect crystal, and the important questions raised: what are these imperfections, why are they so important? And it is very common, the imperfections in the solids or in the other crystalline material or in amorphous material also, and many important properties of material are due to the presence of imperfections. So imperfections broadly, in a broad sense, it may be defined that these are the defects in the crystals that presents when it is solidified into the from liquid state to solid state. And we have discussed that during shrinkage there is always some voids and always some extra space are present into the solidified material when it is cooled to the room temperature. So these defects are the inherent to the crystals. There are varieties of defects are observed in the atomic or ionic arrangement of crystals, and these defects influences many of the properties such as mechanical, electrical, magnetic property, etc. None of these are completely perfect crystals, but often have structural defects which results in different physical and mechanical properties. The metal perfection can be divided into geometric and physical property, and which are divided into three types. These imperfections are divided mainly into three types. That is, first of all, point defects. Point defects or zero-dimensional defects. Under this, vacancy of atom may be present. Interstitial atoms may be, and substitutional atoms. So when interstices are there, there will be a substitution of atoms. So these are broadly comes under the point defects, which is also known as zero-dimensional defects. Then there is that is line defects or one-dimensional defects. One-dimensional defects. These are all edge dislocation and screw dislocations. And there are another kind of defect that is called surface defects or two-dimensional defects or planar defects. Under these, grain boundary defects, twin boundary defects, stacking fault defects, low angle boundary defects, these are all. And in addition to these, there may be defects in the electronic configuration of individual atoms. They have a strong influence on electrical and optical properties of materials. However, in the strict sense, they are not crystal or lattice defects, and hence they are not considered here. So in addition to this, we know that atoms are not in stationary in their designated lattice position, but are vibrating about their mean position. And the frequency or of vibration depends on its temperature. These vibrations of atoms play a fundamental role in affecting certain properties such as specific heat and electrical resistance of the material. So now come to the type of defects or type of imperfections. Zero-dimensional point defects, one-dimensional linear defects, two-dimensional defects or planar defects, which include surface and inner. In addition, three-dimensional microscope features of bulk defects such as formed due to various reasons, that is hole, cracks, and contaminants. So first of all, we will discuss zero-dimension or point defects. These are the most common imperfection caused by loss of some atoms in the structure, which often occurs when the metals dissolved by synthetic disturbance during the growth and redistribution of atom in the structure of the atom. These point defects, all the atoms in the solid possess, a vibrational energy, and all temperature above absolute zero. That is, at absolute zero temperature, the atom possesses a vibrational energy, whatever the small may be. If the temperature raises, this vibrational energy that is increases, and there will be a finite number of atoms which is sufficiently strengthened, sufficient energy of this atom to break the bonds which hold them into the equilibrium position. So when the temperature of the material increases during the various working process or by heating process, this point defects raises. That means the atoms which have sufficient energy to break the bond which hold them into their equilibrium position. So when the temperature raises, the atoms may break the bond and moves from one place to another place from their equilibrium position. Now, once the atoms are free from their lattice site, they give rise to the point defects. Also, due to the presence of impurity atoms, point defects are likely to come into the crystals. See here in this figure, it is shown that is one or more atoms are not in the regular site and they are missing. So that is called the vacancy. And if that atom have sufficient strength to break from its equilibrium, to break the bond from its equilibrium position and moves to another location, that gives the interstitial defects. So now these may occur in the presence of impurity atoms. Point defects are likely to come into the crystals due to the presence of impurity atoms. The most common imperfection in impure metallic crystals as shown in this figure due to the impurity of atoms. And if an atom is missing from its regular site, the defect produced is called vacancy as shown in this figure. That is, in this case, in a regular site, the atoms is missing and it is moved to another location as shown. That gives the vacancies at one place and interstitials occurs in the another place. If the matrix atom occupies its own interstitial site, the defect is called self-interstitial. And if a foreign atom occupies the position of matrix atom, it is called substitutional impurity atoms as shown in this figure also, that substitutional impurity atom is of yellow color. If it occupies an interstitial position of matrix atom, it is called interstitial impurity atom. In addition to these defects, divacancy and trivacancies may exist in the crystal. Next, there are another two type of point defects presents in case of ionic solids, that is called Frankel defects and Schottky defects. Frankel and Schottky defects are forms in the ionic solids. An atom may leave its regular site and may occupy nearby interstitial sites of the matrix, giving rise to two defects simultaneously. One is vacancy and another is self-interstitial. These two defects together is called Frankel defects. This can occur only for cation because of smaller size as compared to their size of anions. When cation vacancy is associated with anion vacancy, the defect is called Schottky defect. Schottky defects are more common in ionic solid because the lattice has to be maintained electrical neutrality. Now, what are the effect of these defects and some of the properties of these effects are need to be discussed. First of all, they increases the hardness and tensile strength. due to distortion of the lattice. They increases the electrical resistivity. Vacancies increases the kinetics of diffusion and phase transformation. These vacancies and self-interstitials are produced during the plastic deformation of metal and alloy and by high energy particle irradiation. Also, vacancy concentration increases with increasing in temperature, and the same can be retained by rapid cooling from high temperature to low temperature. Now next, we will discuss about that one-dimensional or linear defects. These linear defects is also known as dislocations. It is defined a part of line of atom will be missing from its regular site, and this missing row of atom is called as dislocations. The distortion is centered along a line, and hence the line defect is called as dislocation. Movement of dislocation is necessary for plastic deformation. This dislocation is the boundary between the slipped region and unslipped region and lies in the slip plane. The structure and behavior of dislocation affects many of the properties of the engineering materials. The line defects or dislocations have two categories basically. One is edge dislocation and another is screw dislocation. This figure shows an edge dislocation in the matrix where linear defects occurs at the top of the head frame with only a special half plane of the atom. Now this dislocation as shown in figure, the dislocation line considered as the defect due to the insertion of an extra half plane of atom. That is as shown in the figure in the top of the head of the frame. The line defect is also this type of line defects when it is also called positive dislocation, and it's denoted by the symbol of inverted T. This extra plane present in the upper half of the crystal, and if this extra half of plane is below the crystal, this is known as negative dislocation and is denoted by symbol T. The lattice above and below this dislocation line is in distorted state. From positive dislocation, the lattice above the line is in compression, whereas below the line it is in tension, and reverse in case of negative dislocation. The more interatomic spacing below the extra half plane of atom for positive dislocation and above the extra half plane of atom for negative dislocation, and it favors segregation of interstitial atoms and impurities. The dislocation line can also be described by the Barger's vector B as shown in this figure. Barger's vector indicates the amount and direction of the shift of lattice on this slip plane. Barger vectors of dislocation line can be found out by using Barger's loop or circuit method. Barger's circuit or loop is formed by taking equal integral lattice translation in each pair of parallel sides in the region of interest. Such a circuit would close itself in a perfect region of crystal, that is, a region with no dislocation will form. And this circuit fails to close itself in the region containing a dislocation. The closure failure, that is the vector necessary to close the circuit, is called Barger's vector of the dislocation line. For the edge dislocation, Barger's vector is normally perpendicular to the dislocation line. Next, come to the another type of dislocation or line defect, that is called screw dislocation. This screw dislocation can be imagined as being produced by the cutting the crystal a part way through a knife and then shearing one part of crystal with respect to other parallel to the cut, as shown in this figure. The name screw dislocation is given because it transforms successive atomic planes into the surface of a helix around the dislocation line. The Barger vectors is parallel to the dislocation line. Such a dislocation has neither tensile nor compressive stress, but has a shear stress. In general, dislocations are more complicated. However, they can be resolved to obtain their edge and screw components. Dislocation come into the material during the solidification or by mechanical processing of metal. The number of dislocation is expressed by the dislocation density, which is the total length of dislocation per unit volume, and it is measured in centimeter per centimeter cube, or the number of dislocation intersecting a unit cross-sectional area, that is lines per centimeter square. The dislocation density of well annealed material is approximately varies from 10 to the power 4 to 10 to the power 6 lines per centimeter square, and with very careful annealing, it can be as low as 10 to the power 2 lines per centimeter square. It increases with the degree of cold work and can be approximately 5 into 10 to the power 11 lines per centimeter square for a heavy cold work material. Dislocation lines can end the surface of a crystal and at grain boundaries, but never inside a crystal. Therefore, it is clearly indicates that dislocation must be either from closed loops or branch into other dislocations. Now, what are the characteristics of this dislocation? It has strong effect on deformation characteristics and mechanical properties of material. It is very much influenced on recrystallization temperature, phase transformation temperature, characteristics, phase transformation characteristics, electrical properties, and corrosion resistance of the material. With this, today's session we will like to conclude. Thank you for watching this, joining this.